Let's take a look at a concept called optimization, and we're going to explain how to think of optimization through the use of a basic example. Optimization explained using a basic example. Optimization explained using a basic example. So the question we're going to try to answer is this one. Find two numbers whose difference is 100 and whose product is a minimum. Okay? Find two numbers whose difference is 100 and whose product is a minimum. Now, what if we asked for a product that's a maximum? Well, there'd be no limit on that because you could just keep picking two numbers bigger and bigger and bigger that are separated by a distance of 100 and their product would continue to grow. But this is a more interesting question where we want the product to be a minimum, as small as possible. So optimization is the application of finding maximum or minimum values. And we've been through those concepts already using things like the first derivative. So let's get started on this problem and sort of understand what we need to do. The first thing we need to do is we need to define variables, right? So in this case, we have two numbers. Those will be the unknowns that we'll use. So we will let x be the larger number. It doesn't matter which one's larger. And y be the smaller, okay? So that's going to be important to us. So we've got our variables defined. The next thing we need to do is start to describe the relationships in the problem. So the first thing we need to do is look at any known relationships. Known relationships. These typically result in equations. Okay, so x and y are the two numbers, and we know that the difference between those numbers is 100. In other words, if I take the bigger number x minus y, I know that I get 100. Okay? Now the next part we need is we need the product to be a minimum. Now in this case we only have one known relationship, so that's not an issue. So what we need to do next is we need to create a, and this is key, create a one variable function. Create a one variable function. And just because I'm running out of real estate on the board here, I won't write anything more, but on your own paper, you could describe that the function you want to create should be the idea that you're wanting to maximize or minimize. In this case, we want our function to be a product function. So we're going to call it P for product. And how do you calculate the product of these two numbers, x and y? Well, the product is literally x times y. And so the issue here is that this function for product, P, is not one variable. It's x times y. So what we will do often is we will come back up here. We'll come back up here and we'll rewrite this relationship so that one of the variables is solved. Okay, so in this case I could add y to both sides and I could see that x equals y plus 100. And so that's going to allow me to rewrite my product function replacing x with y plus 100. So P equals y plus 100 times y. And now I've got a function with one variable. And what I'm trying to do at this point is find an absolute minimum of this function. But before we do that, let's simplify the function by distributing our y to get y squared plus 100y. Y squared plus 100y. And now what we need to do is we need to find the absolute minimum of this function. And when we do that, we'll come back and answer the question to find the two numbers, okay? So find, in this case, the absolute minimum, if it exists, okay? Find the absolute minimum of that function. Now, sometimes when you have these functions you're doing optimization, you'll have an interval that you're working on, some limitation. In this case, our variable is y that we're left with. So you might have some limitations on what values of y you could look at. And so you might be looking at a closed interval, and you know how to find absolute max or min on a closed interval via the extreme value theorem. In this case, there's no limitations on what y could be. It could be any number. So we have to be a little more cautious in finding the absolute minimum. So the way we do that, if you recall, let me go ahead and erase some of this just to get some space for what I'm going to do here. So if I want the absolute minimum, I've got to find the derivative of the p function. So p prime equals 2y plus 100. And then I need the critical numbers of this. So I need to know where this guy equals 0. So if this equals 0, then y is negative 50. And the derivative here always exists, so we don't have to worry about y values for which it does not exist when we find our critical numbers. So the only critical number we have is negative 50. And so now what we need to do is look at what the derivative tells us about this function increasing and decreasing, etc., to find a potential absolute minimum. So we're going to set up our chart here. So the variable is y, and then underneath that I'll list the values of the derivative, and underneath that I'll list what that tells us about our original product function p. Okay? So let's see, our only critical numbers at y equals negative 50. And then I've got over here y values less than negative 50, and over here y values greater than negative 50. All right, so p prime, when y is negative 50, p prime equals 0. So I'm going to list a 0 there on my p prime row when y is negative 50. If y is less than negative 50, p prime, you should be able to see pretty easily, is negative. And if y is bigger than negative 50, p prime is also easy to see is positive. Okay? By the way, it could help if you factor p prime, pull the 2 out. And then maybe those signs are much easier to determine. And now what does this tell us about p? Well, if p prime is negative, we know that p is decreasing. If p prime is 0, we know we have a horizontal tangent line. And if p prime is positive, we know that p is increasing. So what this is telling us is that from negative infinity to negative 50, the function is decreasing. And at negative 50, it has a horizontal tangent line. And then after negative 50 to positive infinity, it's increasing. So we have an absolute minimum right here at y equals negative 50. We have an absolute minimum, has to be. This particular function is differentiable everywhere. It's a very simple polynomial function, so no weird behavior to worry about. This has to be an absolute minimum. So now how do we answer the question? We have an absolute minimum when y is negative 50. The question here is to find two numbers, and our two numbers are x and y, remember? So we already know that the two numbers are, well, one of those is negative 50. That's your y value. And then x, we have to go back and find the relationship between x and y, which is right here under the known relationships. I'm going to use the one here in blue. When y is negative 50, x will be negative 50 plus 100, which is positive 50. And so these numbers are 100 units apart, meaning their difference is 100, but they have a minimum product of two such numbers that are 100 units apart. And that's the answer to the question. So you'll find your absolute max or min, and then you've got to use the information you get to go back and answer the question that's being asked.